In talking about refracting telescopes, this is essentially how you get the refracting telescope. You have some source at infinity. Remember, we're looking at things way beyond the Earth, so these rays will definitely be very, very parallel. And what your objective is doing is essentially focusing this down at a distance focal length f from your objective. What this does is actually it prevents humans from using a refracting telescope that only has one lens like this. We can still put some sort of CCD spectrometer here, and this would work. But if we are to use our eyes, we actually cannot have all the light converging in a single point. In order to do that, we actually need another lens. And this is the reason why in refracting telescopes, we need an eyepiece. And the purpose of this eyepiece is really just to let you examine the image at the focal plane. If you have just a refracting telescope like this with your objective and then your eyepiece, and you have this extra distance, you need to actually fine-tune it so that your image to your eye looks on focus. But if you have it like this, then you will be able to see the image, but the image will actually be inverted. In order for you to see the image without being inverted, you can actually incorporate a third lens that will actually flip the image again. And the main purpose of refracting telescopes is really just magnification. There are actually a lot of reasons why refracting telescopes are no longer used, especially for science. One of them has to do with chromatic aberration. So what happens is that the refraction of light by a lens will depend slightly on the wavelength of the light. For example, red rays will actually go down and converge at a slightly larger distance to the objective compared to the blue ones. And this means that the focus, the effective focus, is different for different wavelengths. This is really a fundamental limit to the performance of refracting telescopes and is the reason why you can see photographs like this. If you're using a really large lens, you start to see the image is sort of out of focus for some of the wavelengths. The other fundamental limitation for building larger and larger refracting telescopes is to do with the size that you would require. We've mentioned that f number before, the ratio between the focal length, the distance from the objective to where the light actually converges, and the diameter. And it turns out that for refracting telescopes, this number makes it so that when you start to increase the diameter, this focal length is so big that the telescopes become huge. And you can see an example here in Wisconsin that a diameter is just 1 meter, which for modern telescopes is not big of an aperture, but the length, because of the distance where the light will actually converge, will already be 18 meters. And therefore, even telescopes that only have a diameter of something like 1 meter will start to be as large as some of the larger telescopes that actually have apertures of 8 meters. And you can also see an example here of a telescope in the Lisbon Observatory. You might recognize this astronomer, where the length is really large, but the diameter is still quite small. And another big limitation is that these lenses are so big that even with their own weight, the glass will actually start to shift and move and almost behave like a fluid. So that is a big concern long term. And also, these lenses are incredibly expensive. And it turns out that in the Lisbon Observatory, actually, they had the budget to build the entire observatory, and they spent it all on just these lenses. All these limitations are one of the main reasons why modern telescopes are all refracting telescopes. It makes them much smaller, much easier to build, and much cheaper. Refracting telescopes really are a way to eliminate chromatic aberration, for example. They're much easier to make, they're cheaper, and it's much easier to support a large mirror than a large lens. And it's much easier to make sure that a mirror is actually not deforming or it's behaving like a fluid. The cheapest reflecting telescopes are spherical ones. These are even easier to make. They're really, really cheap. But it is important to note that especially if you start to scale them up and have quite big ones, you start to have actually spherical aberration. This is a consequence of parallel rays coming in to your mirror, and actually those that are hitting your mirror at closer to the border will actually be focusing on a closer distance than those that are hitting your mirror closer to the center. So you do have some spherical aberration that leads to images becoming more blurred. You can, of course, correct for this if you use instead a parabolic mirror, where the curvature of the mirror is incredibly perfect to make sure that regardless of where the rays hit your mirror, they always converge to the focus. But of course, even in a parabolic mirror, as we'll see, if you start making them really big, they become really heavy, and even a tiny little bit of deformation could lead to some of the light rays actually converging at slightly different distances. And a way that people now deal with this routinely is through a process that is called active optics, essentially where you put some attenuators at the back of the mirror, and whenever you detect some sort of curvature, you can correct it back. And this is particularly important when you're looking at a target that is really low on the horizon versus something where you're looking at zenith, where essentially the flexure or the own weight of the mirror will actually contribute to some extra curvature. And those attenuators can actually counterbalance it. Perhaps the most famous case of spherical aberration actually happened on the Hubble Space Telescope. You might have heard about that and heard about the fact that when it was launched and it took some of the first pictures, they didn't look that great. I mean, they looked incredibly blurred and probably something you could do from Earth. And the spherical aberration problem was actually a result of this really small error in curvature of the mirror, more towards its edges. So we've seen that it actually would make light rays to converge at different distances from the mirror and therefore lead to something like this, an image that is blurred. But this happened actually during manufacture. So this was not a design flaw. So you cannot blame physicists that were working on this. You can just blame the engineers and the company that did it. Fortunately, in 1993, 3 years later after the launch, these brave astronauts managed to actually go there and put some glasses on Hubble so that you could fully correct the spherical aberration. And after the correction, then the telescope started working perfectly. They also did a lot of other work that meant that the telescope continued to work perfectly. Unfortunately, because Hubble is in a relatively low orbit, a lot of other missions have happened where essentially astronauts have been able to change components, to update them, and also to put in new instruments that really allowed Hubble to continue to be incredibly productive and make so many discoveries that otherwise would not be possible. And of course, talking about going there and fixing a telescope, one telescope we will not be able to fix is JWST. This is sort of the successor to Hubble, even though it's mostly observing things at the longer wavelength. But one of the big problems about JWST is that its orbit that you can see right here is actually very far away from the Earth. There's no way that we're going to go there and fix it. And therefore, the telescope just has to work perfectly, essentially from day one. And this is one of the main reasons why for JWST, people have actually used these huge chambers that mimic space conditions where the optics were fully tested to make sure that nothing can go wrong. And of course, both me and a lot of people all over the world are excited that JWST, the 6.5 meter telescope, will finally be launched this year, 2021. It doesn't look like there will be any further delays. I remember that this telescope used to be scheduled to be launched in 2008. That was definitely very ambitious. This is the most expensive telescope ever built. That's almost 10 billion US dollars. And perhaps one of the things I'm mostly looking forward to is the fact that CR7, the galaxy that I've discovered together with some of my students, will be one of the first targets for James Webb. And it's also one of the reasons why you can find CR7 in all the official web pages and documentations of essentially the most expensive telescope ever built. So once James Webb goes to L2 and it deploys its mirror and its sun shield and everything works, one of the first things I will point out is the galaxy CR7, which should tell us a lot about the details of very early galaxies, including potentially some of the first stars ever formed.